More than 2 centuries ago, in a dimly lit lab in London, two pioneering scientists, William Nicholson and Anthony Carlisle, were on the verge of a discovery that would change the course of energy history. They had just connected the world's first modern battery, Alessandro Volta's voltaic pile, to a beaker of water. They watched with a sense of awe as tiny bubbles formed on the wires dipped in water. Without knowing it, they had performed the world's first electrolysis. The bubbles were hydrogen and oxygen, separated from water using a simple electric current. This unassuming moment in a small lab sparked the beginning of a powerful technology. Years later, a brilliant mind named Michael Faraday gave this process structure. He established the laws of electrolysis, which mathematically define how much electricity is needed to produce a certain amount of gas. His work laid the scientific foundation for everyone who followed, turning a curious phenomenon into a predictable science. The journey of the electrolyzer from a lab curiosity to a global energy solution is a story of innovation shaped by human need. As the Industrial Revolution boomed, the 19th century saw the first alkaline electrolyzers. These were bulky but effective, producing hydrogen for a wide range of applications. In a fascinating early use case, a French military engineer named Charles Renard used an electrolyzer to fuel hydrogen airships, demonstrating the technology's potential for mobility even then. Fast forward to the Cold War era. NASA's ambitious space missions required a new kind of hydrogen source, one that was compact, lightweight, and incredibly efficient. This need gave birth to the PM, proton exchange membrane electrolyzer, developed by General Electric in the 1960s. Designed for the harsh environment of space, it would later become a cornerstone of clean energy back on Earth. Today, we live in an era where electrolyzers are no longer niche tools. They are gigawatt-scale clean energy machines, turning wind and solar power into storable carbon-free fuel. From bubbling glass tubes to high-tech membrane stacks, the electrolyzer has traveled a long and incredible journey. This time, it's not lifting airships. It's poised to lift humanity toward a net-zero future. To truly understand the role of electrolysis, we need to know what it is. It's a fundamental but powerful concept, using an electric current to break apart a compound, in this case water, into its basic elements. Here's how it works. You dip two metal rods, known as electrodes, into water. A direct current, DC, is applied between them. Water alone isn't a great conductor, so we often add an electrolyte, like potassium hydroxide or a solid polymer membrane, to help carry the current. The magic happens as a simple electrochemical reaction. At the negative electrode, the cathode, water molecules are converted into hydrogen gas, H2, which bubbles up and is collected. At the positive electrode, the anode, water molecules release oxygen gas, O2, a harmless byproduct. The result? Pure, usable hydrogen, which can be stored under pressure, transported, or used immediately. It's an elegant process that transforms a simple, abundant resource into a powerful, clean fuel. This is the most critical part of the story. While electrolysis itself is a clean process, its carbon footprint depends entirely on its power source. If you power the electrolyzer with electricity from a coal or natural gas plant, the hydrogen produced is not green. In this case, it's often referred to as gray or brown hydrogen. The pollution simply happens at the power plant, not the hydrogen facility. However, if you power the electrolyzer with renewable energy from solar, wind, or hydropower, the entire process is carbon-free. This is what we call green electrolysis. And the result is green hydrogen. No fossil fuels are burned, no carbon dioxide is released. The only byproduct is oxygen. This distinction is key. For example, countries like India, through their National Green Hydrogen Mission, are making a strategic bet on this technology to decarbonize industries and achieve ambitious climate goals. Green hydrogen produced by electrolysis is more than just a clean fuel, it's a solution to some of our biggest energy challenges. Replaces fossil fuels. It can be used in sectors that are hard to electrify, like steel production, fertilizer manufacturing, and aviation. It can even replace fossil fuels in a car's combustion engine, or in a fuel cell, as seen in cars like the Toyota Mirai, which runs quietly with only water vapor as an exhaust. Energy storage. Solar and wind power are intermittent. They don't produce power 24/7. Electrolyzers act like a massive battery, storing excess renewable energy as hydrogen. When the sun isn't shining or the wind isn't blowing, that stored hydrogen can be used to generate electricity or fuel. This solves the intermittency problem of renewables. While the promise is clear, green electrolysis isn't without its challenges. The biggest is the very intermittency it's designed to solve. Low utilization rates. Since solar and wind aren't constant, electrolyzers often run at low utilization rates, which drives up the cost of hydrogen. Think of it like a factory that only operates 40% of the time. Its products will be more expensive. Cost. While the cost of renewables is falling, the total cost for a reliable 24/7 power supply, including storage, is still high. Since electricity accounts for 60 to 80% of green hydrogen's cost, this is the biggest hurdle to overcome. Infrastructure. Building electrolyzers near renewable sources often places them in remote areas, far from demand centers, requiring new, costly transport infrastructure. But these challenges are being tackled by engineers and innovators worldwide. The electrolyzer has already traveled a long journey. From a simple experiment to a key technology for our planet's future, it's a journey powered by science and shaped by need, and it's now poised to turn water into the fuel of tomorrow, quietly, cleanly, and brilliantly.